finished, cosmology and galaxies were really still not completely merged together. They weren't completely merged together. People like Peebles were already doing both. And there was in Russia Zendovich and some others. But there were very few people doing both cosmology and galaxies. Now everybody almost is doing at least some aspects of both, because you cannot do either alone. So this developed. So I did like my MSc on Big Bang synthesis, which relatively early universe, and my PhD on galaxy dynamics, and they didn't really connect that much. But already there were connections starting with the first fluctuations of the cosmic microwave background, and Kobe and so on will talk about all that. But the first 3 days, today, tomorrow, and Wednesday, we will be talking about the background evolution, the large-scale evolution of the universe, when you consider it as a soup, as a sort of homogeneous gas of galaxies that are not colliding, okay, as opposed to a laboratory gas, without any pressure, as opposed to a laboratory gas. And you do the dynamics of this homogeneous soup, isotropic. Okay. So here's a few useful references. There's some on the website. This is the simplest from a Newtonian point of view. If you want to do GR and follow Dr. Adam's lectures, then try to learn more. I'll touch on the GR, but not very much. But Dr. Adel will give you the basics. So if you want to follow this, these are simple lectures on how you do background cosmology from the GR point of view. And these are things in the middle. And this is the classic work by Peebles, a bit outdated, but very nice. Both Newtonian and GR. And quite careful treatment of both. This is quite advanced, but the first chapter, first 100 pages or so are quite good. Because he was actually Weinberg, a particle physicist who was learning the new stuff in cosmology. So he was very lucid in the stuff he was trying to learn and convey. The stuff he was trying to innovate in, the rest of the book, is not that good for a beginner, at least. And this is like a reasonably simple introduction to cosmology, both and the perturbed universe, also not only background, both GR and Newtonian. So if you, I like to start with this picture a lot. If you Google cosmic history, you'll find pictures like that coming up. And this tells you the current, like say, trendy word, paradigm of what happened since the beginning of the expansion of the universe, which is at some point really far here. And it's supposed to be very, very early, like 10 to the minus 30 or something seconds of that order. After the beginning of expansion, you had inflation, a very an exponential expansion, very rapid rate, which Alexei may talk about, should talk about. And then the universe at that point was very hot, and because it's compressed and things were bumping into each other. There weren't any atoms, because you can't have atoms when things are so hot. And you can't even have nuclei because they fall apart from really high energy. And all sorts of interesting stuff which we will not talk about in detail. You will talk mainly about this part where the universe is cold enough as you can have start to have atoms. Basically, the electrons and protons make atoms instead of being a plasma that is fully ionized. And then supposedly you things start to cluster because of gravity, and then you get galaxies, which are the building blocks of the universe, and we come to it. Now the interesting part is that we can see a lot of that. In fact, all of that, at least to here, because we can look back in time, things that are far away. So you can make telescopes and observatories that either in optical or in other, sometimes radio is very powerful also, especially for high redshift. And you can do also all sorts of stuff, gamma, X-rays, and so on. I look back and gravitational waves nowadays, and look back on all of that. So this picture is not some simple theory. It is a simple theory, but it has a lot of supporting evidence. Okay, but it has there are still many issues. For example, you'll see in this picture, which is less than 10 years ago, I think, maybe 7 that I founded. It tells you the first stars are 400 million years, and we think we are finding galaxies that are 10 to 11 stars, 200 million years, or 300 million years, something like that. Okay, so even though this was the standard thing a few years ago, it is changing all the time. So it's a very fast-moving subject. So as I said, this week we'll talk about so this is a very ambitious project. So we want to tie the galaxies with cosmic evolution and see why they are distributed this way, what is their distribution of masses, sizes, shapes, morphology, that is, how they look like, what sorts of stars they host, things like that. And it ties almost all branches of physics, from fundamental theory here, very high energy physics, far beyond anything you'll get in an Earth accelerator, and quantum field theory on a curved space-time, relates to things how you do quantum theory with gravity, not quantum gravity, at least not here, but getting there. And all sorts of stuff that is more akin to ecology than fundamental physics. Gas dynamics, heating, cooling, thermodynamics, hydrodynamics, heat transfer, all sorts of things to be able to create galaxies in the end. And nature of dark matter, or gravity, or defying gravity, and also almost all branches of physics, from the very fundamental to the very phenomenological. Okay? So first of all, we'll take a little tour of the universe before we describe the background. So just for those who didn't do any astronomy, what are the scales? A scale from the Earth to the Moon is 1 light second, about. The light takes a second to get here. That's why you could hear the Apollo astronauts talking back to each other. They don't wait 100 million years. So the sun is 8 minutes. But already to the nearest stars, it's a few light years, which is a parsec. We'll be talking about parsecs alone, so we should know what a parsec is. What is a parsec? A parsec is, this is the sun, and this is the 8 minutes from the Earth to the sun, average. And this is the diameter of the Earth-Sun, of the orbit of Earth around the sun. Okay? So 16 light minutes about. Okay? You have to go to a distance of a parsec to see that thing look at an angle of 1 arc second. So not 1 degree, not 1 arc minute of a degree, but 1 arc second, meaning 1 over 60 over 60, 3,600, right? Yeah, 3,600 of a degree. So that's how the orbit of the Earth, not the Earth itself, the orbit of the Earth, the 16 light minute looks like. Very small, that's a parsec. And that's how the orbit of the Earth would look like, 1 arc second, 1 over 3,600 of a degree from the nearest star, and that's the nearest star. Okay, so it's distances are quite a lot. So then you have the Milky Way. We are like so that parsec is 3 1/4 light years about. Okay, try to calculate it. It's a very simple calculation. Okay, and this is, by the way, something called an angular diameter distance, which we were talking about. So we are like about 8 parsecs, 8 kiloparsec, 8,000 parsec from the center of the galaxy. This is how the galaxy, the Milky Way, looks like. Okay, it is a galaxy like that. This is another galaxy seen much more at an angle. Okay, this is the Milky Way. We are in the disk. Okay, it's a flat disk, at least the visible part. The visible part of the Milky Way is mainly a flat disk, and we are in it. So if you are inside a disk and you look, it looks like a line. So this is, if you go to the desert and on a clear night without a moon and without lights, you will see this band of light, the Milky Way. This is the galaxy. We are 25,000 light years, something like that, from the center, 8 kiloparsec. Okay? So something like 25, 26,000 light years from the center. And this is the center here. You will see these things here. This is dust obscuration of stars. So this is the Milky Way galaxy. So we are, this is the visible part, okay, of the Milky Way galaxy. So we are already talking about 25,000 light years. So 1 second to 8 minutes to a few light years, one galaxy is 25. And there are many galaxies. These are pictures of galaxies. So there are some that rotate. So they rotate with the centrifugal force being counteracted by gravity. So you have full apart, there's a wave. So an equilibrium between those two. So these are called disks or spiral galaxies. And you have these, which are more supported by random motion, ashwai, against gravity. So you have two modes of doing a gravitational equilibrium, one which is random motion and one which is rotation. And two rotating ones can merge, and they do a random model. So this is important actually in the standard model. These mergings are really important, and there are ways to test, as we will see, whether we are correct in our paradigm or not. So these things are testable. This is the pictures. If the model, the standard model is correct, we need many, many pictures like that. Okay? And we can count how many pictures we have and compare. Okay, so the disk galaxies have much more gas, usually, than these guys. So somehow there's a lot of burning in the middle, and you can see these blue things. It means there are a lot of young stars. Because young stars are blue when they're hot. Things are blue on the Planck spectrum, which we'll talk about also, when they're hot. So blue means hot. Hot stars die fast because they're very massive and they're very hot. They expend the fuel very fast. So when you see blue stars, it means there's a lot of star formation. When you see red stars like this, it means the galaxy is, from the point of view of star formation, dead. It only has old stars. It's not forming new, younger babies. We see only old people. So it's not forming them. And this is a way, by looking at how many blue and ultraviolet shining stars there are, we can know the history of star formation. This is a very important test also, because we have models of star formation. And maybe we'll be able in the end of the second week to talk about star formation rates and things like that. Yeah. Okay? So, and in the center, you can develop big black holes up to 10 to 9 solar masses, maybe a few times 10 to 9 solar masses, which accrete gas, like they swallow gas, the surrounding gas, and shine and give feedback energy. And this is also feedback energy that's very important in galaxy formation. So this is the Hubble sequence of galaxies from Hubble from 100 years ago, maybe even more. So these are the round ones, and some are spherical and some are more elliptical, and these are SO, which are similar to that galaxies, but without gas. And these are the spirals. They also come in types, ones with bigger bulges, almost like these ones, big bulge in the middle and little spiral, and one with mainly disk and gas and so on, and very different. And then some have bars and so on. Now, just to get you from the end, we can simulate this stuff from the initial conditions of inflation and get it correctly. This is the Hubble sequence according to simulations nowadays. This has only developed in the last 10 years, that you could build the Hubble sequence of galaxies a priori from the initial conditions, you know. Now, but it's a bit tricky because there's a lot of parameters they put to get it right. Okay, which we'll talk about later. The ecology of it is very tricky, but they get it right. Here you go. This is simulation computer And this is the Hubble sequence according to Hubble. And these are pictures of galaxies, schemas of galaxies. And here is a simulation on a computer. Hopefully, by the end of the second week, we'll know what these guys do. But I'm just saying that they do, they can. But they always, whenever we look further away at higher times, with bigger telescopes, you can see fainter things, so you can go back in time more. Things start appearing that don't fit the model. So you can build your Hubble sequence and so on, and you want to get your early Hubble sequence in the early universe, but it doesn't work that well. So because you fit your parameters to fit the local one, and okay. So it doesn't always work. What do I mean by that? I mean, these are primordial galaxies from the Hubble Ultra Deep Field. There are now also James Webb. We'll get to that in the end, but they're not as sophisticated, by the way, yet as surveys as the Ultra Deep Field. They're so much better for individual galaxies by far than Hubble, of course, but not much better as statistics yet, because it's only been a year. Okay. So these are early galaxies. As you can see, they don't look like that. They can't really. There are, for example, not many of this type of the flat, nice disk. There's much more of these types, and they're more irregulars. They can't be easily classified. So we want to know how you get from here to here, or from Hubble to here. That's why I put a sign going both ways, depending on how you like. Do we get from the primordial to the local? These are very early galaxies, like less than 1 billion years after the beginning of the expansion. These are local galaxies, 14 billion years. Okay? So you want to know how to describe these as well as these, okay? Both. So you want to do, for example, things like a galaxy mass function. How many galaxies of a given mass or luminosity do I have for a given mass? A distribution function. And you want to do your ethereal observation. So already with Hubble, 7 years ago or 8 or so, the models that we have some discrepancy with the observations. This is what you expect, and there's at the high end of the mass, these are masses, and this is the number. You have more observed and these are different redshifts, meaning different times. So this is like 13 billion years ago. This is like 10, 9, and things like that. These are higher redshift galaxies. And we find that we can fit the distributions of the galaxies with time, but they are not perfect. These are error bars, so it's not disastrous, but with James Webb, it is becoming a bit, problematic. The error bars are coming down, and the systematics are being resolved. So it appears that we have at older galaxies at higher redshift. We'll get to what redshift means and all that. So don't worry about it. Just at older times, زمان, okay, بالبلدي, it appears there are more massive galaxies than models predict. The models that are so successful in explaining the Hubble sequence at z equals 0, meaning t equals now, 14 billion years, are not that successful, or at least appear not always that easily interpretable, to be precise, at higher redshift. Now, it could be a problem of all sorts of calibration and complicated gas physics. We'll get to in the second week, but it could be a problem also more fundamental. So, just to start to understand things, we want to start to make sense. How do we start to make sense of all that? First of all, we look, and when you look at a physical problem this big, you want to start somewhere. نبتدي منين عشان القصة الكبيرة دي. Okay? انتوا خلاص احنا ورينا انها حوسة وعايزين نشوف نبتدي منين. Okay? So where do we start? First of all, let's see from the physics we know what we can apply. That's the first thing you want to do. And you find that on the first order or zero order, gravity is the most important force in all this, and it can teach you a lot about what's happening. And it will turn out that it will teach you simple things that are fairly deep without a lot of the complications that we are due to non-gravitational physics, basically electromagnetism, and also strong nuclear forces that will get into the galaxy formation process itself. So we want to do now only gravity, because why is gravity so dominant? Now, first of all, gravity is very weak. Here's the Newtonian law for gravity, and here's the Coulomb's law for electromagnetism. They look very similar, except for the physical constants. Okay? But if you divide, let's say this is an electron, this is a proton. If you divide, and this is like at 1 meter, if you divide the constants by themselves and the masses by the electrostatic charges, you'll find that it's 10 to the 40 times about. I don't remember the exact number, but about 10 to the 40. 10 أس 40 مرة حوالي. حاجة زي كده. Okay? So gravity is so weak compared to electromagnetism. In fact, and that's why things are very flat, you see.
It's about 10 to 20 something.
No, it depends if it's electron and proton or proton and proton.
Oh.
Okay, electron and proton.
Electron and proton?
Yeah, electron is less massive. But no, I think anyway, it's a lot.
Yeah.
It's a lot. I don't remember. Do you remember? Anybody remembers how much it is?
Right.
Yeah.
But what I'm talking about is the ratio between
Yes.
K and G.
Yeah, but you need to define what the masses
Right.
also.
Yes.
The masses are important. I'm talking about the masses.
If you're talking about the
The forces, yes. Yes. I mean, you put an electron mass here and a proton mass. Okay? And you need that. Otherwise, because these are masses and these are charges.
Yeah, that's different from what I'm saying.
Yeah, I know. Yeah, I know. But anyway, it's really a lot. And that's important. It's really a lot. I'm talking about the ratio of forces, not the constant.
ratio of the
Forces.
The strength of the
Of the forces. For an electron and a proton, and the mass of an electron and proton, and charge of an electron and proton. Mind you, the charges are the same, but the masses are different. Okay? So I'm just talking about this elementary level. So anyway, 10 to the 20, 10 to the 40, I think it's 10 to the 40, but if somebody can Google it.
39. Electron, 39.
39, okay.
Exactly.
Turned out to be 39. Electron, so electron,
yeah.
proton, 37. Okay, so anyway, or 36. Whatever. It's really a big number. Doesn't really matter the exact number. The important thing is that if you have, it means that if you have an atom, if you could have an atom that is gravitationally bound, actually, if you could have an atom that is gravitationally bound, suppose the RMS speed would be something like 10 to the 40 times. For the same RMS speed, the atom will be 10 to the 40 times longer, 10 to the 20. So it will be very big for the same speed. Okay? For the same RMS speed, the RMS radius would be like almost on the cosmological horizon. So an atom would be completely huge. Instead of being 1 angstrom, it will be of the order of billions of parsecs, gigaparsecs. So this is the important part. But the other important part but why does gravity win on larger scales? This is the important part. Why does gravity win if it is so weak? Well, because it's only attractive. Electromagnetism has positive and negative. So there is repulsion and attraction. Gravity only has attraction. It doesn't have any repulsion. Okay? So the positive and negative cancel out. In a plasma, it's on the Debye length, for example, for anybody knows about plasma. But the gravity doesn't cancel out. So it is therefore, and this is very important, this is VIP is very important point, not personal. If there was no opposite charges, you win on large scales because the opposite charges cancel out. Now there are two other forces in nature: the nuclear forces, the weak and the strong, but they are short range. Gravity is long range. So it's long range and attractive, it wins on large scale. And that's very important, okay? So it will hold together stars and galaxies and so on, and will determine to a first order cosmic structure and evolution on all large scales, okay? On all scales of galaxies and beyond. The most important thing is gravity. Because it's very weak, you'll find time scales that are very long, and things that are very fluffy, very small densities, and very long time scales. Okay? Okay, so when you have a gravitational system, like I said, it can have random motions that are counteracted by gravity, because gravity can only bind. Okay? It's only attractive, can only bind. If you don't end up with a black hole or a point mass, you need to have something that counteracts. You can have rotation, you can have thermal motion, you can have random motion with stars, but you need something. And that is expressed in this thing here. This is the potential energy of a ball of radius r, a rough estimate. In astrophysics, you have to get used to order of magnitude, rough estimate, intuitive, Bilwayan estimate. So this is like a ball, and this is a dimensional analysis of a gravitational energy of a ball. Basically. What is a dimensional analysis? We want something that includes G and M and R that gives us potential energy, gives us an energy. Okay? So what is it? First of all, energy is force.dr, so the r squared in Newton's law becomes r. And then this is a binding energy, so Gm times m. Okay? Binding potential energy. It's similar to the Coulomb, except Coulomb you'll have positive and negative. But let's say you have everything positive, you'll get something like that, or everything negative. And this is the total mass of the galaxy. Okay, this is its kinetic energy. This is an average of the squared, which is the variance. If the galaxy is rotating, then this will be equal to V, the total square. If this is not rotating, they're not equal. Because if you have mean motion, this is equal to the mean motion squared. Otherwise, it's not the case. So in a galaxy عش ضبابير زي دي, where things are moving randomly, like in a wasp nest, there is no mean motion, and V squared is not equal to V the whole square. Okay? In a spiral galaxy, it will be. Now you can get time scales from this. You can just put m equals the density r cubed. Again, we don't put 4 over 3 pi. We just put the density times the radius cubed. And you can get a radius, that's very important, a characteristic radius, and a characteristic time. Radius is speed times time. This is the crossing time of the galaxy. The time this collapses if there's no velocity dispersion, and the time that a star crosses the galaxy. Okay? From one side to another. Very important thing about this time is that it's scale free. This is extremely important, and it's for all power law potentials, not only for gravity. Any power law potential, because power laws are very interesting in the sense that cosine AX, for example, does not equal A cosine X. But AX to the power n equals A to the n times X to the n. So you can always take the factor out, and meaning it's scale free. A power law potential or power law force is scale free. GR puts a scale at some things because it puts an additional thing in the speed of light. But here in Newtonian there's no There's no scale. And it's important because then the dynamical time depends only on the density. It does not depend on the size of the galaxy or its mass. It depends on the density, m over r cubed. So galaxies with different masses and different sizes and so on, which have the same density, will have the same dynamical time scale. And for everything, for cosmology too, for everything like that. And this is very important. This is called self-similarity. So this is quite important. Okay? And we find this is called, in a much more formal thing, this is called the virial theorem, which tells you, in fact, there's a factor of 2, formally speaking, and so on, which tells you that the kinetic energy is of the order of the potential. Okay? In order for the gravitational system to be stable, dynamically, not thermally. We want to know about the difference between thermal and dynamic equilibrium and gravity. It's a very complicated issue. You can ask me later. Dynamically, meaning we don't take into account collisions between particles. Okay, that's what I mean by dynamic equilibrium. Okay? And you will find scaling relations in galaxies that seem to go with that trend. In the sense, the trend meaning the virial theorem. You'll find something called the Talley-Fisher relation. This is rotation speed of a galaxy in kilometer per second. And this is luminosity, the light that comes out. Okay? The energy that we see. We will define luminosity and distances and so on quite not rigorously, but we'll talk about it later in some detail. But anyway, this is just for intuitively the amount of light that comes out, which we assume is proportional to the amount of mass in the galaxy, the number of stars that shine in the galaxy. And this is the speed. And this is for the velocity dispersion, the v squared, for the Eshet Dababir, for the random galaxies, elliptical galaxies, spherical galaxies, and this is for the disk, for the spiral galaxy. And both seem to, these observed derivations, these are observations, and these observed derivations on log scale follow with a little tweaking from the virial theorem, so things are quite nice, aren't they? But the problem is, they follow as proportionality. But there is hidden mass. There's extra mass that's not there in these relations. They follow as a proportionality, but the proportionality constant, to get the right scaling relations, you'll need to put extra mass that you don't see. And the reason, who saw this plot, this kind of plot before? Okay, not too many, huh? Okay. So let's draw the speed of gas or stars in a rotating galaxy as a function of radius. Okay? So this is the radius in light years yet, and this is the speed. We find that if only the mass of the galaxy we see, the thing should go down like that. It goes down as Keplerian. The Keplerian speed, Kepler's law, is V proportional to 1 over square root R, like in the solar system. Okay? Because V squared is Gm over R. Right? So if M is fixed and G is the Newtonian constant, is fixed, V is proportional to 1 over square root R, which goes like that. But we see things going like that. Now from 21 centimeter hydrogen, not very important, but this is from seeing Doppler shifts in the lines. Not important now, but we'll talk about it later. Seeing the lines of hydrogen that is rotating. We know it's 21 centimeter, it's a very well-known line. It goes like 21 point something or 20 and so on. So from the Doppler shift, the change in frequency of the عطر بتاع زمان بتاع الفيلم العربي. احنا بنشوف واحد الاحمر لو واحد بعيد وازرق لو جاي علينا. And so you can. So, as I said, galaxies are not very dense. The average density of the galaxy is 10 to the minus 24 kilogram per meter cube. خزان المية اللي عندكم, the water is 1,000 kilograms per meter cube. And this is 10 to the minus 24, the density of a galaxy. Because water is held by electromagnetism and a galaxy is held by gravity. So, that's the main reason, no other reason, but that's the main reason. Density 10 to the minus 24 kilogram, and water 1,000. Air is at 1. And like rock is something like 10,000. So it's like 27 orders of magnitude different than this. The time scales are also very long because it's very fluffy. So a galaxy will take every 100 million years. A Milky Way, a few 100 million. The mass scales are something like from 10 to the 7 to 10 to 13 masses of the sun. So they contain 10% of that of order is visible and the rest is dark. This is determined by thermal physics we'll get to in the last lecture. This is not determined by gravity, at least not only gravity. Part of it is thermal physics. Most mass particular region is dark. The nearest galaxies like Andromeda, the big galaxy, is a few megaparsecs. So we're talking here about millions of light, right? The nearest galaxy. So we got from 1 second to minutes to years to thousands of years to millions of years. And galaxies, you could say, well, we did all this Newtonian stuff. Where is the relativity? Where is the GR? Well, there isn't really, except for the center, the black hole, the massive black hole. Because galaxies, we saw the rotation speeds and the typical speed. Rotation speeds are 100 kilometers per second or 200 and things like that. 300 max, maybe 400. So V over C squared is like 10 to the minus 6. So the motion under gravity is very small. And also the pressure for an elliptical galaxy, random motion, is very small. Pressure is rho V squared over rho C squared, which is what is determined a relativistic pressure. So 10 to the minus 6 also, so very small. Okay? Now, except gravity can make very strong things because if you let it dissipate and completely lose energy and fragment and contract all the way to making black holes and things like that, can make huge densities and velocity and so on because it's only attracted, but it does not normally, but it can. So therefore, nothing is relativistic except when that happens, when things can dissipate and contract and become very high density. So gravity is very weak, and typically velocities and density are small, but when there is enough dissipation, like in the center of a galaxy, then it's a very different ballgame. And then it's relativistic, but not for the stuff we would be interested in this course, except some parts which I'll denote. Okay? So let's look at larger scales. We looked back in time and so on. We want to look at larger scales. This is a cluster of a galaxy. These are groups of galaxies making a cluster. It's like an elliptical galaxy to some extent, but now instead of being made of stars, it's being made of galaxies. Thousands of galaxies for the bigger clusters. Okay, like Perseus and so on, maybe 10,000. And then if we look at even larger scales, this is like of the order of a gigaparsec, 10 to the 9 parsec. 10 to the 9, so a few times 10 to the 9 light years. We went from a light second to a light minute to a light year to thousands of light years to millions. We're getting to billions. So this is a picture of the sky, of the whole sky from something called the two-mass survey. And these are clusters, and they have names: Coma cluster, Perseus cluster, Abel clusters, and so on. After people, sometimes, like Abel, and this stuff like that. But on the very large scales, we tend towards homogeneity, the Shoiba and which we think is a reflection of the primordial soup. And we think it's a reflection of the primordial soup. What does it mean, homogeneous? It means if we start picking boxes that are of the order of 10 megaparsec or bigger, around, certainly of 100 megaparsec or bigger, somewhere in between, and count the number of galaxies in these boxes, we'll find that they are about the same. The difference in the number of galaxies in the squares, let's say here on this picture, count the number here. Let's say we find 1,000 and a number here. We'll find 1,100, say, if the box is of the order of 20 megaparsecs. And then here 900 and so on. It's about the same. We will say that delta rho of the rho is small. Or delta n over n. Let's not get wrong in business. It is complicated. Right? So delta n, meaning the difference between 900 and 1,000, 1,100, 950 and so on, compared to the 1,000, which is the average, is small. So this is when we start talking about cosmology. We move from galaxy and we start talking about cosmology. So as a rough rule of thumb, we leave galaxies and talk about cosmology when delta n over n becomes 10%, 20%, things like that. Less than 1. So. In a galaxy, delta n over the difference is of the order, delta is of the order of 200. I will get to why we say 200. There's a reason, theoretical reason. So how do we do these things? In the last 20 years, there have been many surveys counting the galaxies in the sky and their redshifts, which we'll talk about, meaning their distances. We count the distances and numbers. Local, meaning things that are a few billion megaparsecs or light years, not things that are, up to the very early. So this, the two big ones, the 2DF, and the bigger one, the Sloan Digital Sky Survey, surveyed like 3 gigaparsec cubed, and this is the square of it. So very huge distance. This is like 10 billion light years. 10,000 million سنة away. Okay, really a lot of stuff. So this is how the cosmic web looks at. These are galaxies. Every point here is a galaxy. There are clusters, and then there's the filaments and so on, which we'll explain hopefully next week. And on the larger scale, we get the homogeneity, like I said. Count here and here and here, you more or less get a homogeneity. So this is a picture of the telescope. Its main point of the telescope that it has an image and take very many galaxies at the same time. It's pixelized in a way that it can map the sky very well. It was made for that purpose, the telescope. Not to get the internal structure of galaxies as much as to make maps. Now I participated in a medium deep survey a long time ago that does this kind of stuff, but at redshift 1 or 3/4 of the way to the beginning of the expansion. But it was very small angle. It wasn't like this 3 gigaparsec. It was like an angle of 2 degrees squared. Euclid, which was launched a week or 2 or 3 ago, would do this kind of thing up to the 10 billion years ago. Not the local universe like Sloan Digital Sky, but we'll do these maps over time up to 10 billion years ago. Okay? So, but this is the state of the art now, the Sloan Digital Sky. So Euclid will do much beyond that. So that's how we know. And this is a radio picture, really on very large cosmological scale. This is in the radio, pictures of cosmological distances. And you can see the homogeneity here. Quite, there's no question about it. This is the homogeneous soup of the universe, because the smallest, these are galaxies points, and the smaller, this is a picture of the sky in angles, what they call declination and so on in astronomy. But these for our purposes are angles, theta and phi, of the whole sky projected, where of radio sources and the radio frequency observations of many different telescopes that are the least galaxy between every galaxy and the other. There is the distance of at least like 10 or 100 megaparsecs or something like that. So you don't see the cosmic web at all. You only see the large scale homogeneity. And you can see it's large scale homogeneity. And this is a zoom in. So even if you zoom in a bit, you start seeing a little bit of the cosmic web, but not much. So at these scales, which are horizon scales, really, you see like of 10 gigaparsec order, which is the maximum we can see, really. Homogeneity comes out. So we want to try to describe, first of all, a little going back in time, there's this thing about Olber's paradox. Who heard about Olber's paradox? Anybody here? Oh, one person. Olber's paradox goes back to Kepler and Edgar Allan Poe, the poet. So why, if there are so many stars, they didn't know there were galaxies. Why, if there are so many stars, is the night sky dark? I mean, the light goes as 1 over r squared, and we'll get to it if we have time. Gravity, like gravity, the intensity of light goes as 1 over r squared. But these shells of stars, they go over r squared. So if you stack them up, then you will have very high surface luminosity. You will see as if you are on the surface of the sun or a star. So we should be millions of degrees. We should be, if everything is stacked up to infinity, so if the universe is infinite in extent and infinite in age, we should be baking of Nuala, because all the stars will be sending their light. So what's the solution to that? The solution to that is the universe is not infinitely old, and or was expanded, so that the light energy decreases with time. But the most important, perhaps, is it's not infinitely old. If it was infinitely old and infinite in physical extent, it should be burning with radiation. Because simply you stack up all the stars are sending their energy and the galaxies, and you stack them up, you'll find really huge amount of energy. But it's not there. So this is important. Okay, so we want to do Newtonian cosmological evolution quickly of the last 15 minutes. I cheated it. So we want to do cosmological evolution of this thing. We want to do dynamics of this big, large scale. Not the dynamics of galaxies or clusters and so on, but of the homogeneous soup. We want to see what happens to it. And if it's true, it's of finite age, how did it evolve? How does it move? And that's part of the dynamics. And we're going to do classical dynamics, Newtonian dynamics, classical and Newtonian. No relativity. We'll do a bit of relativity slightly next time, but for now, just Newtonian. So Newtonian, the main difference between relativity and Newtonian mechanics is the finite speed of light. One of the main differences, but a very principle. For us, it is the main difference, and that the field is not strong, but it's not anyway. The difference here, for our purposes, is the finite speed of light. So you'll have, if you want to do Newtonian, you need to take small patches where the communication time between the galaxies is small. The communication time is small because they are near each other. So you take small patches. Okay? You take this universe of ours, this soup, and take small packages that are big enough. You need to take them big enough. You've probably heard that before in statistical mechanics and so on. You take it big enough so that it's homogeneous, but small enough compared to the total, the horizon, so that the communication time, the time that the galaxies talk to each other gravitationally through the speed of light, is small. Compared to what? I'll be more precise maybe later today or tomorrow. Compared to what exactly. But anyway, we'll take it small enough. Right? So that Newtonian mechanics work. Otherwise, because Newtonian mechanics assumes instantaneous communication. Gravity has infinite speed. And GR assumes speed of light. So if you want to do Newtonian, you need to assume small things so that the limit is Newtonian limit is observed, and weak field which is observed. Okay? And by definition, because it will be small also, so the mass of your patch is small. Now, why does it work? First of all, because cosmological principle we are assuming, and this Einstein assumed it and others early 100 years ago, but now we have plenty of evidence that the cosmological principle actually is satisfied. Meaning we have homogeneity and isotropy. Isotropy meaning all directions being the same. So a sphere is isotropic. That doesn't mean it's homogeneous. The density of a sphere can change over radius. Rho equals rho of r. but it's isotropic. You can also have homogeneity by no isotropy, but like a homogeneous crystal that is not isotropic in access, but its density is constant beyond the atom. So you can have, but the universe that is isotropic at every point is also homogeneous, potentially. So any point is a center, so we can take any point. And finite age, meaning that a finite patch is isolated. This is important also, because otherwise the Newtonian energy will diverge and you'll have problems with it. Okay? And also, you cannot say we have a sphere, because nothing in a sphere is an infinite unit. You will not have any Newtonian forces at all, and they will cancel out, it will diverge and cancel out. And Newton thought about that, and he had a problem making a cosmological model. So, but we have a finite patch where the speed of light travels at a small time scale. So we'll get rid of that problem, because we'll age of finite and we make a patch very small. And all patches are contract the same way. So the dynamics is scale-free, because like in the galaxy, this is gravity too. Dynamics is scale-free, so they all travel the same way. So no patch goes into another patch. So you maintain the homogeneity in isotropy. So that's another reason. So basically, we'll be looking how to expand this into that self-similarly. Self-similar. Yeah? Things transforming into each other in time. So how do we do that? I don't always say I should say Gauss theorem. I do, but I will still do the other stuff. Okay, so Gauss theorem. Here's the Earth. If the Earth didn't have rocks, which we assume the galaxies don't collide and don't have electromagnetic force and things like that, it will simply collapse on a dynamical time, square root of 1 over 0, 1 over square root 0 to collapse on that time. But it doesn't, because it has rocks. But okay? So why does it collapse? Because there's a gravitational field on the surface of the Earth. That's why. You are sitting and I'm standing because there's a gravitational field. How much is this gravitational field? Who knows that the gravitational field is that, where m is the m of the Earth? Who knows that this is the gravitational field that is per unit mass that is holding you, the force per unit mass that is holding you in the chair? You don't? Why? This is news for you. You are held on the chair because there is a gravitational force proportional to the mass of the Earth and inverse proportional to the radius of the Earth.
They all know, but they are lazy to say.
Hi. They know Gauss theorem also. Okay. So Gauss theorem says that, this force projected on the area surface of the Earth is equal to the mass inside. In electrostatics, it's equal to the charge. Here, we replace the epsilon with 4 pi g, because we are doing gravity. Like in Coulomb's law, we replace 4 pi epsilon naught with g, 1 over 4 pi epsilon. Okay. So it's always normal because it's a sphere. So the integral is trivial. You can do it directly also. You can calculate this directly by dividing the Earth into shells, and then dividing the shells into rings, and then summing all up. It's a bit of a laborious exercise, but it's straightforward. It's not difficult. Or you can cheat a bit and use Newton's shell theorem, which says that the gravitational field outside a spherical shell, a spherical shell, is like a point mass, like that at a point mass at its center. This is Newton's theorem. So you can do it in many different ways to know that the gravitational force per unit mass at the surface of the Earth is equal to the radius of the Earth and its mass. Mass over the radius squared, okay, with a g. This holds for the Earth, it holds for the galaxy, and it holds for Newtonian cosmology. Because the gravitational law is universal. At least that's what Newton said. Yeah, so it holds for everything. It's not only tying you to the room here, or tying the solar system, it ties the galaxy and ties cosmology. So we can use it for cosmology, at least under the conditions I state, okay, for the Newtonian stuff to learn. Mahmoud? This is next time. Okay, this is the second bit that you guys had problems with in the last years. What about if we were inside the Earth and there was more mass outside? Does it contribute to the field or does it not? It doesn't, because something that was discovered by Newton, and in GR there's some analogous theorem discovered by Berkeley, a mathematician and dynamical systems theorist also, in addition to being a relativist. So basically the reason, if you are here on the surface of the Earth and there's more Earth outside, or the atmosphere, or whatever you want, the force due to every element on that spherical surface outside is counteracted by another element on the other side. Now I found it always quite intuitive. We just say this area is proportional to r squared, and this is r1, and this is to r2 squared, and the gravitational law is inverse r1 squared and r2 squared. So I find it very intuitive, but I wrote it here explicitly so that you guys can work it out. You'll find that this is basically an area of the base of a cone, pi r1 squared times sine theta. Here, theta is this angle, and this is the same theta by Euclidean geometry, opposite equal angles, okay? And this is plus and this is minus, and they are exactly the same. The r squared cancels out, and you're done. Okay? هاي المرة دي خلاص ضاعت. يعني صعب يعني نشرح أكتر من كده. You can look at the slides. Okay? So you end up with this dynamical equation F equals ma, where this for unit mass, per unit mass, you take the m out, and this is the a, and this is the f. Okay? So this is, okay? And we're going to do it for cosmology. Right? So this is the last thing. So this is our dynamical equation for our Newtonian patch in an isotropic homogeneous unit, okay, of finite age. And we have an energy integral. You should convince yourself that d by dr of dr by dt squared over 2 is equal to d2r by dt squared. Okay? Convince yourself that d by dr of this thing, okay, is equal to that. That means you can integrate the two sides over r, and this is trivial, okay? Just 1 over r squared becomes 1 over r, and this becomes that. This is called an energy integral. Okay? This is dynamic because, as Alexei was saying, because our equation don't have explicit dependence on time. This is a function of r only. So we have energy conservation, which is a constant of integration. Right? And this is called an energy integral. This is basically our cosmological equation by the way of it. It's that simple. But there will be a lot more input before we can do cosmology. But this is basically our cosmological equation. And it is like an equation of a ball thrown up from the Earth. Exactly. Because if this is the mass of the Earth, and this is the radius of the Earth plus the radius of the ball going up, radius of the Earth plus the radius we throw up, this is exactly the equation of a ball that you throw. So usually in your room, the ball will go up and then go down again. But if you throw it really hard from Cape Canaveral, or you have a very, Newton calculated this, if you had a very big cannon, the ball wouldn't come back. And he calculated it easily, it's called escape speed. So, therefore, in this very toy model, we haven't put a lot of stuff, mind you, in But it is the basic cosmological model. This is a very bastardized form of something called a Friedmann equation. But we're not there. Very minor. But it is. Yeah? You can either have a universe that expands like a ball coming down, and it is exactly the same equation, where this is the energy. But what is this energy? We'll know later. What is this energy exactly? You have to do a bit of GR to know what this energy is. Or, yeah, you both, Newtonian and GR. And this is the ball not coming back again. The Newtonian example, a cannon that just escapes. Things that escape, like the Voyager spacecraft escape completely. They escape the solar system. Okay? So these are the different, very basic Friedmann universe. One expanding and recollapsing, one expanding forever, and so on. Next time we'll find that this constant, the scale-free dynamics, this thing here is manifested in the constant, in all shells of our sphere expanding the same way, regarding of radius, and that the energy over the radius, this radius that is still arbitrary, are a constant. Okay, but this we'll start talking about next time, okay? Because this will start moving us into a more serious cosmology. But for this time, this is our main equation for the evolution of a Newtonian patch of matter only, no radiation, no exotic universe with ball with energy E inside a given ball. Okay? So it can be a universe that used to be called a closed universe, still, but I'll tell you why next time. It's called a closed, open, and so on. But from the Newtonian point of view, we talked about, it's like a ball coming up and down. Ball means energy is positive. Ball escaping marginally, energy is zero. Ball escaping to infinity, energy is negative. Positive energy means you're bound. Negative energy, you're unbound. Okay? So this is from the Newtonian point of view. You can have an expanding universe forever, unbound, and you can have recollapsing universe bound. Okay? Okay, that's enough for today. Any questions? Why, that was simple. Yes. First of all, it's not heat equation. If you linearize it, I want to see stability, but it's simpler than that. You don't need to linearize it. You have the book solution. I can actually write it down. This is called, when you solve this is actually something that the novel from there, I feel a solution. It's called cycloid solution, which we'll get to by the way. These are called cycloid, they're very simple. So you have a good solution